your slope field, you should have something that looks like this on this problem. You'll find that derivative by plugging into the derivative that they give you. You should get 1/3. You'll have your tangent line, and you should get 7/6 whenever you solve that out all the way. And then for the last part, your final answer is y equals 2 minus 3 over x. And I found C first, but you can do this where you solve for y first and then find C. It just depends on what order you like to do that. Alright, questions? Then you'll walk through this last part. Okay. Alright, so our equation, our differential equation was dy over dx equals 2 minus y over x. So we're looking at 2 minus y over x. So to separate these, you could cross multiply x dy equals 2 minus y dx here. And basically you're going to have to divide this side by x. And you're going to have to divide this by 2 minus y. So you end up with either dx over x, or you could write it as 1 over x dx. And over here you've got 1 over 2 minus y dy. Are we okay separating? All right, then you must integrate both sides. Both of these sides are going to be natural logs. On the right-hand side, it's just going to be natural log of x. On the left-hand side, you are doing a u/du substitution. I did not write all the steps there, but your u over there would be 2 minus y. So your du would be negative dy. So you need a negative here, which means you got to put a negative out front. And so when you integrate that, it's just going to be natural log of the u, which is your denominator. So you get natural log of 2 minus y. And you have that negative out front where you had to do that u/du substitution. And so I went ahead and plugged in the number here. It's up to you which way you want to do it. But I plugged in my 1 and 3 for my x and y, because we know f of 3 equals 1. Natural log of 1 is 0. So this just goes away right here. And you're going to subtract that natural log of 3 to move it over to the other side. So you end up with the negative natural log of 3 being your c. And so I divided everything by -1 to get rid of that negative right there, which changes your signs over here. So it's natural log of 3 minus natural log of x. And then I also used a property of logs here. Natural log of 3 minus natural log of x is going to be natural log of 3 over x, like that. And so then if you do e to the power on both sides, the natural logs just cancel, and then you'll just solve that for y. So whenever you have natural logs, our properties of natural logs tell us if you're subtracting 2 with the same base, that you're just going to divide there. If it was addition, then it would be 3 times x there. you could have solved it for y first and then found your c. It's not, I wouldn't necessarily say it's easier either way. I mostly did it this way because I was looking at the answer key that did it that way, but you could do it either way. Okay. For the multiple choice, number 2 should be B. Number 3 is A. And number 4 is D. So B, A, D. All right, so for 2, you've got dy over dx equals x minus 2, y minus 2. So you multiply both sides by dx. And then you need to get rid of that y minus 2, so you divide both sides by y minus 2. Like that. So that's going to give us dy over y minus 2 equals x minus 2 dx. We're okay here? Okay. So when we integrate both sides, this is a u du substitution, but the u would be y minus 2. So the du would just be dy. So you don't have any numbers that you have to deal with here. You're just going to get natural log of the absolute value of y minus 2 on that left-hand side. And over here on the right-hand side, you're just integrating using that power rule. So Emerson, when we integrate that, what will we get? Good. And then the 2? Minus 2x. And then we'll put the plus c on the end. And one thing at this point that we probably start doing is you maybe like integrate one part, but then you might like take the derivative of that 2 and it's 0. So you got to be careful not to get those mixed up here. At this point, you're going to do e to the power. So y minus 2 is going to equal this c right here is going to go out front as your big C, e to the 1/2 x squared minus 2x. And then you'll add the 2 over here to this side. So just by process of elimination, you should probably throw out C and D before you even look at your initial condition. You also, like, you got this plus 2 over here, and you're only finding the C. So if you had to guess right now at this point, if you were out of time and had to guess, B would be your best guess because it's got that 2 right there. There might be some ways it could end up being A, but it's not going to in this case. So our equation is y equals CE to the 1/2 x squared minus 2x plus 2. We know our initial condition is for 5. So we're going to plug in 5 for our y. And 4 for our x. So 5 equals CE to the, this is going to be 1/2 of 16, which is 8, minus 8, which is going to give us a 0. What is e to the 0? Just 1. So C just ends up being 5. Shouldn't be getting 5, should I? Should be getting 3. What have I done wrong? Oh, plus 2. But that still is going to be wrong. Oh, I see. Okay. That should have a plus 2 on the end. I've lost it. I should subtract that 2, making this a 3. And then, so that's a 3 there instead. That fixes it. There we go. I do this really badly, and when we do Newton's Law of Cooling, which we're going to look at today, there's a big chance you're going to forget it too, because it always has a plus number on there that I leave out a lot of times. Okay. All right. Other questions? All right. Let's move on to what we've got for today. So look at those notes that I gave you. We're going to look at some applications. My neighbor was born on leap year, and he's really like my neighbor. He's really, I'm going to guess in his 60s, but I think he just has turned 16. Yeah. I think it would be really cool. I think it's the coolest birthday to have. No, I think it would be the coolest day to be born on. Right. Okay. All right. So let's look at our notes that we have today. We're going to look at several different applications for differential equations, and there are a lot. As I was telling you guys before, if you major in math or even if you do engineering, a lot of times you've got to take an entire class on differential equations, and there's a lot of applications for this. I don't know if we'll have time. There's one video that I have assigned the last couple of years that's really cool, that shows how they model like infectious diseases with the differential equations. It uses 3 variables, so it's a little bit above what we do, but it's something like you guys could probably follow along with because it's a simple version of it. But I'm not sure if we're going to have time to, but I may post it just so you guys can look at it sometimes if you want. But they did the video like 2 years ago whenever coronavirus was started, and it was right at the time we were doing differential equations, so it's kind of neat. So there's a lot of applications for this, and a lot of them are going to start with direct proportionality. Sorry. I've already. All right. Okay, so for this first example, or well, to go back to direct proportionality, I think we might have talked about this a little bit, but two quantities, x and y, are said to be directly proportional if x equals ky, where k is some sort of constant, and really the x or y's could be switched here in this case. I think we looked at this a little bit in the introduction of this as well. It also, another phrase you may sometimes see is varies directly, so you might want to write that down. So that's another phrase that you may see, and it's going to mean the same thing as directly proportional. Sorry, we cannot change. Alright. So, the amount of bacteria in a petri dish increases at a rate proportional to the amount present. At time t equals 0, the amount of bacteria in the petri dish is 10 grams. At time t equals 2, the amount of bacteria in the petri dish is 30 grams. What is the amount of bacteria in the dish at time t equals 6? So, all of this stuff at the end, we're going to need in a minute, but what we're going to have to do first here is come up with, we'll have to come up with a differential equation to start with. So, we did this in the very first part, but it's been a long time since that because we had to stop for midterm and do all of those things. So, the amount of bacteria in a petri dish increases at a rate. So, we're talking the rate at which the amount of bacteria increases. So, and then you can see we have time over here, so we're probably going to be increasing at a rate with regard to time. So, we need to come up with a variable to represent the amount of bacteria. What letter do you guys want to use? A or B? Let's take a vote. A's? B. All right, B's have it. So let's call it. Let's let B be amount of bacteria. Okay. So dB dt is going to be the rate at which the bacteria increases. It is proportional. This doesn't say directly proportional, but if it doesn't say directly, assume it means directly proportional. It's proportional to the amount present. We're going to assume that means amount of bacteria present. So that means it's going to be proportional, which means we're going to have K times the amount of bacteria, which letter should we use for that? B. Okay. So this is our differential equation. Not really. It has a few. Not so much, because in related rates, we've got to take a derivative. This would be kind of like what you would get if you took a derivative of the original function. These are sort of the inverse of that. We're starting from a differential equation, so it's like almost like we're starting from our related rate equation, and we're going back to the equation. Yeah, we're integrating related rates. So before we can integrate, we got to separate our variables. I can't do anything with that dt in the bottom, so I'm going to multiply by dt. So I got dB equals kb dt. So, what do I need to do now? I need to divide by that b, because I have to separate my variables. I could take the k with it, but life is going to be easier if you leave it where it's at. Okay. All right, so now, to me, it confuses me a little bit sometimes when I have that k there, because k is a variable, but it doesn't match the b or the t. But that is okay, because k represents a constant here. So we treat k like it's a 7, or like it's 4, or like it's, yeah, it's essentially a c. Kind of, but we're going to have a c also. So you can't change it to a c.
Wait, if it's a constant, c is a constant, then wouldn't it be the same?
They're different constants.
Well, how? You can have different.
Yeah. So we now need to integrate both sides. What will we get when we integrate dB over b? Natural log of the absolute value of b. What do we get when we integrate k dt? What if I integrate 3 dt? This is not related to the problem. It'd be not x because my variable is t. So it'd be 3t plus c. K, we've got to treat it like it's a 3. So it's going to be kt plus c. Okay? So far. So far. Okay, so I probably want this solved for b instead of having that natural log. So how do I get rid of the... I can't drop them because I don't have an e on the other side. But I can raise both sides to be powers of e. It is going to give me a b. I will make this a big C e to the kt. This should look familiar. Alright, so ket should look similar to an equation that you use a lot in Math 3 and Pre-Cal. Your continuous growth formula is PE to the RT. So these essentially are the same. So here's some good news about all of this. It is assumed in AP Calculus that if you see this phrase right here, that if you set it up and realize that your derivative is equal to a constant times a variable, like we see right here, it is okay to skip all of this stuff and go straight to CE to the KT. As long as it's strictly a directly proportional relationship. So there are going to be, so it has to be, your rate has to be proportional to the amount. So it has to be rate proportional. Yes. So if it says the rate of whatever you're talking about is proportional to the amount of that value, then it's okay to go to PE to the RT or CE to the KT, however you want to call it there. For pretty much anything. It's for pretty much anything. But we're going to see some other problems here soon where we can't skip that because we're not, it might be directly proportional, but it's not directly proportional to the amount. It might be directly proportional to the product of the amount and something else. So we'll see some, I'll show you some problems where you cannot skip. But in the future, it is okay to skip straight to the PE to the RT. And we'll do some more problems like this so you can tell. So if we know we've got B equals CE to the KT, we have two pieces of information that we need to plug in. So at time t equals 0, bacteria is 10. So that tells us that when t equals 0, B equals 10. So if we take those values and plug them in, 10 equals CE to the K times 0. What is K times 0? And what is E to the 0? 1. So 10 just ends up being your C. So now we've got B equals 10 E to the KT. We also need to find the K, that's our rate that we're going to have there. And then once we find it, we can plug in 6 to get our answer. So we got more information that we haven't used yet. What is that? At t equals 2, what does B equal? So if we plug that information into our equation, 30 equals 10e to the k times 2. And this time we're trying to solve for that k. This one's a little tougher to solve, but we can do it. How would we solve that for k? Divide by 10. E to the 2k. How do I get rid of that e? Natural log, so natural log of 3 equals 2k. And we'll divide by 2. So we can do that in our calculator. I do want to show you this on the calculator if I haven't already. Okay, so natural log of, go back to the home screen. Natural log of 3 divided by 2, green button before you hit enter. We should get 0.549306. I would suggest doing this for this problem. You need to use the exact value and not a rounded value for this. Even sometimes even sometimes this value may not be good enough because depending on what numbers you're plugging in, because exponentials, if you round for an exponential and then plug in a number, your error is going to increase exponentially when you plug a number in. So, have I showed you guys how to store a number as a variable on here? Okay, so you're going to hit STO, which is, so we got the number we want right here. We're going to hit STO, which is store, and store it as a letter. I'm going to store it as K because that's what I've called it right here. But you could store it as anything. Don't store it as an X because then it'll be saved as your X, and when you type things in to your Y equals, it won't work as an X. So don't do that. But any other letter should be fine. Don't use X or Y. So I've stored that as K. So our equation is Y equals 10e to the 0.549306t. So if I want to know this whenever t equals 6, which is what the question asks us for, we'll do te to the 0.549306 t to 6 times 6. So 10 e to the, this is where I'm going to tell it alpha k, so I don't have to do anything there, times 6. You could use the answer button too. And so I will get 270. Exactly what it looks like. So. I feel like it's odd that you would normally get that exact number that I got there, but that's what I got. I don't think I messed up. I stored this number right here as my K. So then whenever I type this in 10e to the K times 6, it's using that number right there. Yeah, so I went back to this equation that I had right here, and I plugged in that value I got for K right there for the K. So then I have an equation. I guess I should call this B right here. I did, which hopefully is right. I feel a little nervous about it because usually you do not get full numbers for this. It has a decimal there, which makes me think that it is like 270.00072 or something, where it just doesn't.
Yeah, just don't miss like all the decimals.
Yeah.
Would you want us to just round it to 270?
You have to be correct to 3 decimal places. So if the calculator rounds it to 270, definitely just put 270. If you are, if you actually have to round it yourself, make sure it's correct to 3 decimal places. So you would never want to round less than that, unless the problem tells you to do so. Sometimes it may tell you to round to like nearest whole bacteria. In general, for me, yes, but if it is a free response question on the AP Calculus exam, go to 3 decimal places unless it specifically says to round to something differently, because you have to be correct to 3 decimal places on the exam, unless it tells you to round differently.
I hate when it says like round to the hundreds and then you get like a flat number.
Yeah.
It's the worst.
Yeah. Then you think you've done something wrong.
It's like round to the hundreds, you got like everything.
Okay, questions? All right, so this is really just exponential growth. You do these problems in pre-cal, but we don't start from the differential equation. We start from the PE to the RT. So we might need some review, but you have done something like this before. All right, let's talk about Newton's law of cooling. Okay, Newton's law of cooling is one of my favorite things that we do because I think it's so cool, and it has a lot of forensic applications that you can apply. Coach would have you guys do videos on this. Yeah. Karma. All right, so Newton's law of cooling in pre-cal, Coach Wood gave you the differential equation already solved. But to do that, you have to introduce a couple more variables. And we are expected to do this from the calculus perspective. So we will start with the differential equation. So this will be a little bit different, although still kind of similar to what you guys did with Coach Wood. So the rate of heat loss of a body is directly proportional to the difference in the temperatures between the body and its surroundings. So this has lots of applications. Dead body situations it's going to apply to, but it could also be, we're also going to look at some stuff like if you have something cooling off. So, for example, over at the glass plant, my brother-in-law works there, and they temper glass, so they got to heat it up really, really super hot, and then they've got to cool it down really quickly. And that will temper the glass. So that would be a situation where Newton's law of cooling would apply, and lots of other applications. So we're going to look at some. We'll look at some like forensic applications. We're going to look at some really important applications later about hot pockets that could save you.
They're always frozen.
Yeah.
They're always frozen in the middle and then super.
Yeah, if you've seen, oh gosh, what's the comedian that talks about the hot pockets? I think he's so funny.
Jimmy Fallon?
No.
No.
Gosh, what's his name? I'll see if I can find it. It may be I'll rewatch it and see if it's appropriate. We might watch it. It's just a short clip. Anyway, all right, so let's talk about setting up Newton's law of cooling first. So the rate.
Jim Gaffigan.
That's it, Jim Gaffigan. Yeah. He's funny, and he also talks about the fact that hot pockets are either frozen or molten lava hot in the middle. So we're going to see how Newton's law of cooling can help us with that. The rate of heat loss of a body is directly proportional to the difference in the temperatures between the body and its surroundings. So we're going to let T be the temperature of the object or body, we can call. And then I'm going to use a T sub A for the ambient temperature. Ambient temperature is your temperature of your surroundings. So, like the ambient temperature in this room is probably like 72 degrees, 70 degrees, whatever it is. If you're in a freezer, it's going to be much colder if you're, we'll see. So, do you know my mother-in-law keeps her, in the wintertime, keeps her thermostat on like 61 or 58, or it's like always right around 60.
We keep our house at 80.
Yeah, I see.
Yeah. Save on your energy bills. Going green. Your parents are going green. No air conditioning, yeah. All right, so the rate of heat loss, dt, d, lowercase t. Lowercase t, what is it? Time. Is going to equal, is proportional, so I'm going to put a K here. And it's not proportional just to the temperature, it's proportional to the difference in temperatures. So I'm going to do T minus T sub A. So this is your Newton's law of cooling written as a differential equation. Coach Wood gave it to you as the differential equation was already solved. We are going to, we could go ahead and solve it and just use the equation Coach Wood gave to you. We are going to plug in a number here for TA first. We need to know, all right, so let's just look at this application. We'll see. So this was just setting it up. This was not, this is the rate at which the temperature is changing with respect to time. Okay. So, a dead body is found in a walk-in cooler in a restaurant at 6 a.m. So, somebody arrives at work to find someone in the cooler. Really? Oh no, where do you work?
I thought she said somewhere.
Somebody that works there? Okay. He came back to life, they brought him back. Oh. Yeah. Okay, so this is a realistic situation here. Some of you guys, thankfully, somebody Narcaned him in time to not have to do this investigation. But had there been no Narcan, you probably would be doing this instead of taking him out on a stretcher. So that's interesting. That this is happening. Okay, so the cooler is kept at a constant 35 degrees Fahrenheit. Newton's law of cooling becomes much more difficult if this is not a climate-controlled situation. So, for example, if you find somebody outside at the park, it's going to be more difficult to apply because the temperature overnight was probably not constant. It probably got colder over the night. But if you find somebody in a temperature-controlled environment, you can assume that it was the same temperature, especially in this case, it's a walk-in cooler, so it should stay the same for this whole time. If you had it tracked where you could have an equation for your temperature, you could, but it would make it significantly more difficult. Yeah, so, and it's always sort of an estimate, but it's pretty accurate. So I'm sure they have constants for like a human body, but I would imagine every human body would be a little bit different because everybody has different muscle mass, fat content, all of those things, height, weights, all of those, body shapes. So, in general, an accurate way to do this, because Now, they may have, like if you actually work on a forensic team, I don't think somebody is, like, on scene doing this. They may have, like, constants that they assume for people. But if we want to know exactly, when the body is found, it has a temperature of 72 degrees. So you would need to take the temperature of the body, and then you would need to wait a specific amount of time and take that temperature again. And then you're going to find that K, that constant of cooling, specifically for that body, because it may be different for everyone. They may have a K here. I'm not sure how much it varies, so they may assume that K in like actual real life situations, because it might not vary as much as it could. So, but we want to be very precise here. So, estimate the time of death. Assume the person had a normal body temperature of 98.6 degrees while alive. Okay, and there's another assumption that's like going to give you a little variability. Your temperature may not have been exactly that, but you pretty much have to assume that to be able to do this problem. So, we're going to do dt over dt, capital T over lowercase t, equals K times T minus, what is our ambient temperature in this case?
72.
Nope.
65. 35.
It's a 35. It's the temperature of the environment that the person was in. So, okay, so we're going to solve this differential equation. So we multiply both sides by dt. And remember, capital T and lowercase t are different variables in this problem. So our variables are not separated. We got to get rid of this capital T, so we're going to divide it over here. So we got dt over t minus 35 equals K dt. So we're just dividing both sides by that t minus 35. We're okay here. All right, let's integrate both sides now because we have our variables separated. Remember that K is a constant. We're going to treat it like it's a 3 or a 5 or a 7, not a variable.
So it would be natural log of absolute value of t minus 35.
Very good. Plus C. And so this is a lot like the exponential equation that we just did, but it's going to be just slightly different because we're going to do e to the power on both sides. T minus 35 equals C e to the kt. And over here, the difference is that instead of just having a variable here, we've got t minus 35. So we got to move that 35 over to the other side. So t equals C e to the kt plus 35. I probably would on these. I think you'd probably be okay if you skipped to this. Most of the time, when you see Newton's law of cooling, they may give it to you so that they just give you the differential equation from the beginning. So you would have to show those steps. Right. Right. If it was just the t, we'd skip straight ahead. Okay. So much like the last problem, we're going to use the information that we have. When the body is found, temperature is 72. So when the body is found, that's our t equals 0. We're going to let it equal our t equals 0. And then capital T is 72. So we're going to plug that in. 72 equals CE to the K times 0 plus 35. So that E to the 0 is just 1. It's going to go away. We could subtract this 35. So we get 37 equals C. So now our equation looks like this. T equals 37. E to the KT plus 35. What's our next piece of information that we have? 20 minutes, we got 65 degrees. So that's when T equals 20. Capital T equals 65. So we're going to plug this information in to find our K. So 65 equals 37 E to the K times 20 plus 35. Be careful not to lose your plus 35. I always do. Mess it up. We'll subtract that 35 first. So we got 30, 37 E to the K times 20. Divide that 37. So 30 divided by 37. We're going to run out of time.
Thank you, calculator, for that help information.
Yeah, 0.8108.
That's what I
You can pack up if you want, but keep watching just to see. We'll do natural log on both sides. 0.8108 equals 20K. We'll divide by 20. Natural log of this. Oh. Alright. You'll get a value for your K. You'll plug it in. We'll finish it up tomorrow because we're running out of time. I was not going to give you homework tonight anyway, although I was hoping we could get more of these done. What I want you to do tonight, because you do not have any homework for me, is start at least one of those FRQs. Try to do at least one tonight. Okay? Yes. So we need to find C and K. You're in general always going to find C first. Yeah, so we found C and we plugged that in. We're plugging it into what we started with, and then we can use that other information. All right, do an FRQ for me tonight.